Okay, last week we started talking about exponential functions. And an exponential function is where your x is actually the exponent. And we talked about these being called transcendental functions instead of algebraic functions. And when we start solving the equations for these, you'll see they don't work like regular functions, which is why they're not called algebraic functions. Alright, then we started looking at applications of exponential functions, which got into exponential growth and decay, okay, and compound interest. And so last week we worked on, of course it's not on here because that was on a different kind of video, but you have it in your notes. We used this problem and we figured out how much money she would have if the interest was compounded semi-annually, which is twice a year, monthly, which is 12 times a year, and then daily, which would be 365 times a year. Okay? And then we got into talking about when you're compounding, you can see the difference between compounding annually and semi-annually. There's more difference than when you get down here where you're compounding daily and hourly. You can see that, what did we figure up? That's like a 9-cent difference. Okay? And then we had talked about the natural base E, which is like 2.78 something. And that's going to get into continuous compound interest. Okay? So for principal, and now we're on page 6 of the notes. If a principal P is invested in an annual interest rate, R, which in decimal form, so if it's 6% it'd be 0.06, and it's compounded continuously, then the balance A in the account after T years is given by. So A represents your balance after the continual compounding. P is the amount you started with, your principal. E is our natural base E, that 2.78 blah blah blah, it's an irrational number, the decimal never ends. R being your rate in decimal form, and T the number of years. Okay, so now we're going to use this formula right here. Okay, alright, so suppose Christy finds an account, this is example 5. Suppose Christy finds an account that will allow her to invest her $300 at a 6% interest rate compounded continuously. If there are no other deposits or withdrawals, what will Christy's account balance be after 20 years? Okay, so we need to identify what we have here. Okay, principal. What is our principal in this problem? 300. It's going to take me a little bit to get used to this. Alright, what is our R, our rate? What's our interest rate in decimal form? 0.06, because 6% is 0.06. Alright, and then do we have the number of years, our T? 20. Okay, so A, the balance, will be principal, this is this right here, principal, which is 300, E, we'll do that in the calculator, which is 2.78 blah blah blah, to the 0.06 times 20 power. Okay, so we can go to our calculator and plug that in. Let's see if I can minimize this. I should already have my calculator open. Have you done it already? What'd you get? Yep, that's right. 996.04, but I'm going to show on the calculator here how to do it. Okay, so I'll go to calculate. Alright, and it's 300. Here's the button right over here to the left of the 1. E to the 0.06 times 20. 996.0, and we round it up to 0.04. Oops, that's not what I wanted to do, but I'll fix that later. Alright. So equals 996. Come here, Stacy. 0.04. What'd she say?
She was just when it was grade. Like at first she was gonna put on the drop in, but then like she said it might mess my school up.
Okay. So did she change it like right now?
Yeah, she said she wanted to email her story.
Okay, so what she wants you to do right now? Going out there?
She wanted to go on.
Okay. Alright, I'll be seeing you in the hall and stuff. Okay. So that wasn't too bad. Okay, so exponential growth or decay formulas. Okay, now this will work not just for interest. Okay, so in here, instead of P, which is the beginning amount of what you're in, when you're doing interest, P is the amount of money you're investing or whatever. Well, here they don't call it P, they call it N sub 0. That means the initial amount, the initial quantity. It's the same as what P was a while ago. If it grows or decays at an exponential rate, either R or K, depending on which one you're looking at, as a decimal, so your rate is still going to be as a decimal, so if it's 6%, it'd be 0.06. Then the final amount, N, that was what our A was in our other problem, after a time T is given by the following formulas. Okay, so your initial quantity times 1 plus R to the T power. It's a growth rate if your rate is greater than 0, and if R is a decay rate, then R is less than 0. Okay, so in other words, if it's a growth, you're going to put a plus R. If it's decay, you'll put minus R. Okay, then continuous is where we're going to have the E involved. You have the initial quantity times E to the KT power. Well, K is your rate times your time. And if K is a continuous growth rate, then K will be greater than 0. If K is a continuous decay rate, then K will be less than 0. Alright, so, and down here it says, watch out, using rates of decay. Remember to write rates of decay as negative values. Alright, so let's go to this real world example on the next page. Okay, this is a population question, not an interest question. Okay, Mexico has a population of approximately 110 million. If Mexico's population continues to grow at the described rate, predict the population of Mexico in 10 years and 20 years. Okay, and A, we're going to do 1.42% annually. Okay, so let's get the information that we have here. Okay, first of all, we're going to be using from the previous page. I wish that was on the same page. We're going to be using the exponential growth or decay. It's not continuous. Okay, so we're not going to be using the continuous, just the regular one. So our formula is going to be N equals the initial quantity, which is N sub 0. Alright, and it's growing. So it's going to be 1 plus r to the t power. If it was declining, it would be 1 minus r to the t power. Okay? So do we have an initial quantity? What's our n sub 0, our initial quantity? What are we starting with? What's the population? 110 million. Okay? And what is our R? What's our rate on part A? Good. 0.0142. Alright, and then what is our time? So we're going to do 10 and t equals 20. We're going to do both. Okay, alright, so let's plug that in. We have n equals n sub 0 is we're just going to do 110. Then when we get our answer, we'll have to put it in millions, okay? So we have 110 times where's my Alright, 110 times 1 plus what? 0.0142 to the 10th power to do the first one. Alright, so put that in your calculator and tell me what you get. Let me see if I can pull my calculator back up pretty easily here, hopefully. Yes. So we have 110 times 1 plus 0.0142, which that would just be 1.0142. You could just do that rather than put 1 plus, to the 10th power. So what do we get? Alright, well what we're going to need to do though is put that in millions. So that'd be 126 million, or 126 comma 656 comma 869. We'd round it. We'd need to round that one. Alright, so it would be 126 million 656,869 in 10 years. Okay, now we've got to do it for 20 years. So basically it's going to be the exact same formula. N equals 110 times, and I'm just going to put 1.0142 to the 20th power. Because that's what 1 plus 0.0142 is, right? So if you put that in your calculator, what do you get? And really what you can do is you can go up here, hit enter, and then just change that to 20. So 145,836,022, right? So that was 145,836,022 in 20 years. Okay. Alright, any questions about that one? Okay, and let's scroll down and look at part B. But I think my video time is about to run out, so I'm fixing to stop it and I'll start a new one.